Welcome to Relativity 102, Galilean Relativity in Depth. In Relativity 102, we'll cover space-time diagrams, the space-time displacement vector, motion in different inertial frames, the Galilean transformation, and the metric tensor in Euclidean space. Much later in the series, the metric tensor will help us explain black holes, the expansion of the universe, gravitational waves, and many other predictions of relativity. But for now, we're just going to cover the metric tensor in Euclidean space. Remember in Relativity 101, we stated the Galilean principle of relativity, which means that the laws of motion are the same in all inertial reference frames. An inertial reference frame is just a non-accelerating reference frame, such as a scientist standing still on the ground, or a car or plane traveling by at constant speed. In Galilean relativity, different inertial reference frames will disagree on an object's velocity, momentum, and kinetic energy, but they will agree on time, space, and mass, and Newton's laws of motion and gravity. Now, I should mention that even though different observers will agree on the size of objects and the space between objects, they will disagree on the position of objects, which is denoted by x all on its own. The main goal of Galilean relativity is to figure out how to calculate all the different quantities that people disagree on in different reference frames. That way, even if a physicist is doing a physics calculation while standing still on the ground, other observers in different reference frames will still be able to agree on how the laws of physics cause objects to move, even if they are doing calculations from different perspectives and end up with different numbers. Now, there's one central mathematical idea that will help us calculate all these different quantities in different reference frames. And that key mathematical idea is the vector, which for our purposes is basically just an arrow. Vectors can represent all sorts of things in physics, like position, momentum, and velocity, and for that reason we'll be using them all the time in relativity. I'm hoping you already know that we can scale vectors. For example, if we multiply a vector by the number 2, that vector still points in the same direction but becomes twice as long. And if I multiply a vector by the number -1, it keeps the same length but reverses its direction. I'm also hoping that you know how to add vectors. If we add a bunch of vectors together, then we get the result by placing them one after another, tip to tail. And we get the result by starting at the tail of the first vector and ending at the tip of the last vector. We can use vectors to describe the separation between two points in space. For example, if we have a pencil sitting on a table, we can describe the separation between the pencil's eraser and the pencil's tip using basis vectors. The basis vectors we'll use are called Ex and Ey. You may have heard of these vectors before, but called by other names, such as x hat and y hat, or maybe I hat and j hat. But their names aren't really important. Ex gives us 1 unit of distance in the horizontal direction, and Ey gives us 1 unit of distance in the vertical direction. And we can add together Ex and Ey in different amounts to get from the pencil's eraser to the pencil's tip. In this case, the separation is given by 4 horizontal vectors and 3 vertical vectors. Writing this in algebra notation, we get 4Ex plus 3Ey. But we can also measure this pencil using a different pair of basis vectors. For example, a pair of basis vectors that's rotated by some angle. Vectors Ex tilde and Ey tilde. And using these basis vectors to describe the pencil, we find that the pencil is equal to 5 Ex tilde basis vectors and 0 Ey tilde basis vectors. Now, there's a really important idea going on here. We see that the pencil separation can be described in 2 different ways, using different numbers, depending on which basis vectors we're using. We can express the pencil in terms of the Ex and Ey basis vectors and get the components 4, 3. Or we can expand the pencil in terms of the Ex and Ey basis vectors and get the components 5, 0. Now, the pencil is a physical object, and it's not changing. However, the pencil can have different components if we use different coordinate systems. And if you can understand this simple idea that the same object can have different descriptions in different coordinate systems, I think it's safe to say that you already understand Einstein's theory of relativity. All we need to do now is just spend a few more videos filling in the details. In Relativity 101, I gave the example of how a muon particle that's stationary will live for about 2 microseconds on average before it decays. But that same muon, if it's moving close to the speed of light relative to the Earth, scientists on the Earth would observe the muon living for about 20 microseconds, 10 times longer, because of time dilation before it decays. And this sounds pretty crazy, but it's not that hard to explain if we use vectors. If we observe a muon creation and its later decay in spacetime, the separation between these two spacetime points can be measured using vectors. With this coordinate system, the decay time is measured to be 2 microseconds. But in another coordinate system, the decay time can be measured to be 20 microseconds. The time dilation effect seen in different reference frames is just the result of using a different vector coordinate system. This is almost the exact same thing as measuring the pencil using different coordinate systems and getting different components as a result. The only difference is that for the pencil sitting on the table, our vectors are measuring 2D space, whereas for the muon decaying in space-time, our vectors are measuring space and time, using x and t. So when I say that understanding the idea of different basis vectors giving us different components for the same physical separation is the same thing as understanding Einstein's relativity, I'm really not exaggerating all that much. This is the central idea behind time dilation and length contraction. And we'll start learning the math behind these spacetime separations in the next part of Relativity 102, starting with spacetime diagrams.